Hi, Mr. Pepperell here, and in this little video we're going to think about current and potential difference in parallel circuits.
So we previously looked at a type of circuit called a series circuit, like the one that's shown here in this diagram. Okay, so there's a series circuit there, and in this type of circuit we found that each component in the circuit followed one after another. Okay, and we also found out that by adding more components to the circuit, like more bulbs, like I've got in here, okay, so adding more bulbs to the circuit resulted in the voltage of the power supply being shared out across the different components in the circuit. Okay, and in real life that's a problem, because what happens is by adding more bulbs to the circuit, it causes them to go a bit dimmer. You share out the voltage, okay? It causes the bulbs to go a bit dimmer. So more components share the potential difference, which means there's less energy for each component. However, in real life, we can avoid this problem with a different type of circuit if we use a parallel circuit. So in a parallel circuit, just like the name suggests, parallel circuit, the different components, and by that I mean the bulbs or the motors or the resistors or whatever the components happen to be, are placed on separate branches. So this is our main part of the circuit, but then the circuit branches. One goes this way, one goes this way. So the components are on separate branches of the circuit that run parallel to each other. Got one branch going along here, and this one's running parallel along up there. Okay, just like if you think about it, okay, the sport parallel bars there. Okay, the guys' two bars are going along straight next to each other. They never touch, never get close together or further apart. They're parallel bars, and this is, with the two branches, a parallel circuit. You could have two branches or three branches or four branches. As long as they all go along parallel to each other, it's a parallel circuit. So let's see how this actually affects the different properties of the circuit, such as the current and the potential difference and the voltage. So firstly, let's have a little think about current in a parallel circuit. Well, if we have a look at this circuit here, okay, just take a little minute to look at that and see what we've got going on there. Okay, we've got a power supply, we've got a selection of resistors all set up in parallel, and we've got ammeters measuring the current at various stages on the circuit. Okay, so we can see there are three separate parallel branches, all with different value resistors. Okay, and you should realise that the resistors will result in a fair variety of resistances along those branches. Okay, the bigger the resistor, the lower the current's going to be. Okay, so that means that because we've got a variety of resistors, we've got a variety of different currents flowing along the different branches here. Okay, if we actually measured the current along those three branches using these ammeters here, we've got ammeter 2, ammeter 3 and ammeter 4. If we measured the current along there, we would find, for example, that the current in this ammeter was what would it be? Let's have a little think of it. It would be 6 amps in this ammeter. Okay, if we measure it in the second ammeter, down here, ammeter 3, we would find that the current there was 4 amps, and if we measure it in ammeter 4 at the bottom here, we would find that the current was 3 amps. So you can see there that the bigger the resistor, the lower the amount of current flowing along the branch. But if we then went and looked at the current on ammeters 5 and ammeter 1, like the one over there, okay, what we'd find is that we'd get a current of 13 amps there, and we get a current of 13 amps on that ammeter there as well. Okay, so what can we see? Well, you should be able to see, hopefully, if your maths is good enough, that the current along these separate branches, these three separate branches here, okay, that the separate currents along the parallel branches all add up to the current through the main part of the circuit. Okay, so we've got 6 amps plus 4 amps is 10 plus 3 amps is 13. So we've got 13 amps going through the main part of the circuit, and that current then splits and different amounts run through different parts of the circuits. So basically what we can say there is that the total current through the whole circuit is the sum of the currents through the individual components of the circuit. So that is current. Well, what about potential difference in parallel circuits? Okay, well, if we look at another circuit here, here's a parallel circuit. Just familiarise yourself there. We've got a power supply, and I'm measuring the voltage across that power supply, and again a selection of resistors along with different branches, and I've connected up voltmeters across those resistors to measure the potential difference there. Okay, well, if we measure the potential difference across the components connected in parallel, we'll find the potential difference for each branch is the same as the supply. Okay, so if up here I measured the potential difference across the supply and I found that potential difference was 12 volts, if I then measured it down here on voltmeter 1 on the first branch, I would find that that meter would also say 12 volts. If I measured voltmeter 2 down here, this one, I would find that that voltmeter also says 12 volts. And again with the last meter, 12 volts again. Okay, so if it's a 12 volt power supply, voltmeters 1, 2 and 3 will all record a potential difference of 12 volts. So to sort of sum that up in a sentence, we can see that for components in parallel, the potential difference across each component is the same. So we know a little bit about current and potential difference in circuits here, but just to sum it up a little bit, okay, we've seen that the potential difference across all components is the same in a parallel circuit, and that the current is actually split between all the different branches. Okay, well, how much current flows down each branch? That's the question here. Well, it depends on the resistance of the components on that branch. Okay, the bigger the resistance, like we saw a minute ago, the smaller the current. And in fact, we can actually work out what current is flowing if we know the potential difference of the power supply and we know the resistance of the components, because we can rearrange an equation that we've come across before. Okay, I can work out the current down any branch if I know the potential difference, okay, and I know the resistance of that particular branch, the components down that branch. And of course, we can simplify that even further by saying that I equals V over R, with I representing current measured in amps, V representing potential difference measured in volts, and R representing resistance measured in ohms. Right, so let's have a go at applying some of these things we just found about. So I've got a circuit here, okay, which is just a power supply set up with a 3 ohm resistor and a 6 ohm resistor that are set up in parallel. Okay, so which one will pass the most current? Which one of the two resistors? Well, it's going to be, we hopefully can tell just by looking at it, the 3 ohm resistor, because that's the lower resistance, so more current should flow through that. Okay, and if we actually use the formula of current equals potential difference over resistance, and we know that the potential difference of the power supply up here, for example, is 12 volts, okay, we can calculate the current. We should actually be able to calculate the current through those two resistors. So for the 3 ohm resistor, first of all I'm going to do is divide the potential difference by the resistance. So that's going to give me 12 volts, because that is the potential difference of the power supply, and in a parallel circuit that potential difference is seen across all components in the branches. Okay, so we've got 12 volts divided by 3 ohms, that's the resistance, which tells me that flowing through this branch there's a current of 4 amps. What about for the 6 ohm resistor? Well, we just do the same sum, different numbers. Again, it's a parallel circuit, so we've got the same potential difference across the components down the different branches. It's a 12 volt power supply, so there's 12 volts across this resistor. So it's just 12 volts divided by the 6 ohms in there, which gives me a current of 2 amps. So there we go. As we said, the smaller resistor, this one here, had the largest current.
Okay, so that is current and potential difference in parallel circuits. And remember, you need to be able to apply the rules we've talked about when you're doing the calculations. It's not just a case of doing the calculation or knowing the rule. You've got to be able to apply the rules when you're doing the calculation. As ever, any problems, don't hesitate to tweet me at Mr_Pepperell on Twitter, and I'll get back to you ASAP. Thanks for stopping by.